and he is going to be talking about the Long Wavelength Array Radio Observatory. Get his talk up here.
There we go.
Greg,
are
you there?
Am I unmuted? Yeah,
we hear you.
Am I unmuted? Can
you hear me?
Okay,
we
great.
do.
Okay, so I'm going to be talking about the Long Wavelength Array, which is a relatively recent radio telescope. We've heard that there's a lot of interest in looking at long wavelengths, especially the redshifted H1 signal that could tell us about cosmic dawn. So given all that interest, what can we learn from the ground? Think of this perhaps as a forerunner to the Lunar radio telescope that Joe Lazio was just talking about. Okay, so getting going here. The LWA is meant to be an instrument that covers much of New Mexico in order to get a good resolution. Arc-second sort of resolution, one needs to go to baseline lengths of about 400 kilometers. So we would have arc-second resolution and Millijansky sensitivity. That's kind of our ultimate goal. We're not there yet. What we do have, though, is the first station of the long wavelength array has been built, and we're running it as a university radio observatory. So this station consists of 256 dual polarization dipoles spread out over about 100 meters, and you can see it there in the top. Let's see if I can get my oh, there's the, okay, so, right, so here's the cursor. Okay, so, and then we send the signals over to a bunch of expensive electronics in this shed over here, and this allows us to take this array and form 4 beams. So we can actually point 4 places at once in the sky. Each one is a modest bandwidth of about 16 megahertz, but there's 2 tunings, so we can cover about 30 megahertz with each beam, and then we have 4 beams. And we also have, in addition to the 256 scans that you can see here, there's 5 outrigger antennas placed up to 500 meters away. Those are useful for calibration. We're also going to use them to try and get a detection of the cosmic dawn, the integrated sky signal, and look and see if we can see that absorption feature that you've seen in many slides today, this morning. Our science is that we do with the array is more than that, though. We're also doing a number of studies on transients, pulsars, the sun, Jupiter, the ionosphere. We are on the ground. We are faced with that challenge of the ionosphere, but while it gets in the way for some people, it's actually interesting for others. So I'm going to try and just give you a quick overview of some of the scientific results that are coming out of the instrument. Here's what it looks like. The dipoles there and the electronic shelter in the background. They're about 5 feet tall. Here's the science that we've done in the past about 18 months, and we've been, of course, a lot of commissioning observations. Hot Jupiters, looking for extrasolar planets. It's very much a popular thing to do these days, so we've been trying that. A bunch of solar system studies, pulsars, another thing that we can do, and I'll just roll through some examples in a little more detail. Let me mention this is looking at the sky, so certainly you're interested in redshifted H1, but you need to understand the foregrounds. It's going to be one of the major challenges for these experiments, and so we are getting a better handle on our foregrounds. There's a poster by Jace Dowell also talking about it. So this is just one megahertz from 52 to 53. Here's the sky. Here's some of the bright sources that Joe Lazio was talking about, Cass A, Cygnus A, seen here a little bit better resolution as we're using the long wavelength array station 1 instead of the demonstrator array that he showed. So anyway, for more information, check out this paper by Jay Stow or his poster. Another way, so we were imaging the whole sky all at once from 10 to 88 megahertz, but that is not we can't read that out continuously. So we have another all-dipole mode where we read out continuously, but only a fairly narrow bandwidth, about 100 kilohertz of bandwidth, but we do it continuously, and that's gives us an all-sky imaging capability. It's running on this computer behind me, but anyway, you can check it out yourself in real time. If you just go to lwa.unm.edu and look for LWA TV, you can see the sky overhead New Mexico right now. So we're looking at that all the time and seeing, what's up there, what's out in the sky. Here's a couple of interesting transients that we've seen over the last few months. So these are sources that have just popped off. Here's a couple. So there's one, a source appeared, and over here is on the right is the light curve for the source. So it rose quite bright, got up to about 1,000 Janskis in a few seconds, and then faded away over the course of about a minute. That happened here, and then in a different part of the sky, we had another one of these events, and again, so bright source appears and then fades away over time. We're studying. We're just in the process of going through all our data and trying to find all these objects and understand where are these coming from, how often are they happening, how bright, things like that. But that's just to give you a flavor of one of the things we learn about by just monitoring the sky almost 24 hours a day. Let's see. Okay, so here's a movie of what we can do if we tune to one of these TV channels, one of these pesky TV channels, then we could see a bunch of things. You'll see airplanes. There's a bunch of interferers along the horizon. Here's a plane going by up here. And then this cross marks the position of the International Space Station. And so watching the International Space Station fly by, and we can see it. We've actually done some further processing. We've got new movies, and it looks more spectacular than it did there. But basically, I think I can, I don't know if I can, yeah, there it goes. Okay, right. So we can detect the International Space Station. Maybe we can look at other space debris. Pulsars are very interesting objects, neutron stars, and we've recently detected a millisecond pulsar. So we've detected many slow conventional pulsars. We've recently been able to detect a millisecond pulsar, and this is the lowest frequency. We've detected all the way down to 41 megahertz. This is the lowest frequency detection of a millisecond pulsar. And we can see that the pulse shape evolves in time, and use that to study the medium around the pulsar as well as the physics of the pulse itself. Moving right along, the Crab pulse is a famous pulsar, and it occasionally emits these giant pulses. We can see them as several per hour, and this is a plot of the spectrum against time. So we've got the spectrum on the y-axis, and then we're going on time, and you can maybe see that there's this dispersed pulse. To help you to guide the eye a little bit, there's also some interference from a couple of television channels, but let's ignore those. Okay, so to guide your eye a little bit. There's two pulses, and they sweep with frequency and time due to the dispersion from the interstellar medium that they're passing through to get to us. So the Crab is pulsing. Maybe there are other sources that are pulsing out there, and we're actively looking for those. This gives you at 4 different frequencies. Looks like those didn't, the labels are a little miffed, but anyway, so going from sort of the upper end around 80 megahertz down to about 40 megahertz, how the evolution of the pulse shape changes. This is detailed in a paper by Steve Ellingson. So here's a little bit of the science of studying the ionosphere. The LWA-1 is quite a sensitive instrument. We can see 1,000 meteors an hour, and so Joe Hemboldt did a study. Actually, it's been submitted, where we look at all these meteors that ionize, impact the Earth's ionosphere, that create little ionosphere trails. And you can see lots of trails in this. This is a composite of a couple of hours of observations, and all these little spots are individual meteors. Some of them are bigger, some of them are smaller. These long streaks are airplanes that flew through. Anyway, so we can look at these meteors, and we can then look at how the meteor trail moves after it's created, and look at the Doppler shift of it, and see the speed, so we can map out the wind speed in the upper atmosphere. That's the science return of that particular endeavor. So I'll summarize and just say that we have the LWA-1 as an operational world-class instrument. There are lots of ways it can be used for pulsars, transients, for cosmology. It's also a pathfinder, and we're learning about algorithm development. How do we process these images? How do we make better images with these large N arrays, such as we may eventually want to do from the surface of the moon? And we're an open skies observatory, and welcome anybody who has ideas, what they'd like to pursue, to get in contact with us or submit a proposal in response to one of our proposal calls. Thanks.
Thank you, Greg. Really interesting. I particularly love those images of the International Space Station, and I'd actually like to ask, you mentioned that you might have even better, more refined ones. I would be keenly interested in getting those movies. I think that Bill Gerstenmaier, who you heard earlier if you were on the NASA town hall, I think that he would just love to see those. So
yeah, great.
If you wouldn't mind sharing those, I would love to pass it on, fully attributed, of course.
Oh yeah, absolutely. There's a number of advantages we have in the radio in this, is that one is that, of course, we can observe 24 hours a day. Another is we can see the whole sky. And a third advantage is, since these are narrow lines, we can Doppler track. And that's how we improve the image, is because we can learn about the velocity of the spacecraft. So it's really kind of a 6-dimensional view.
Yeah, interesting. Well, I look forward to getting those. Thank you so much.